This is lesson 6.3b. I think we're going to get into some geometric distributions here. So let's talk about this one. So this is a binomial distribution, the shape, center, and variability. So a table shows the possible values and corresponding probabilities of, this is blood type. This is the one we were doing before. So if you calculated using the binomial theorem, calculate the probability of 0, probability of 1, probability of 2, 3, 4, and 5. If you added up all those probabilities, it would add up to exactly 100%, if that makes sense. Remember that the chance of success was 0.25 here. So in this case, the shape would look like this. If we graph this on a histogram, just took those data points there. You can barely even see it, but at 5, there's a 0.00098 chance there. So there's a very small bar there. But the most popular bar was 1 was the most popular answer, 39.5-ish% there. And so just a picture of the distribution of, if you have, 5 kids, how many, that's what the distribution would look like as far as the binomial distribution of that one. Which kind of makes sense, right? We think that 0.25, so 1/4 of 5 is like 1 and 1.25. So the mean should be somewhere around 1.25, which it looks like it probably would be. It looks like the median's at 1 there. But how would you describe that? So I'm describing this. So it is skewed to the right, has a mean of, with p equals 0.25 and n equals 5. So that's, you're using the n and p values to describe it in that case, and just describing the shape. So if you want to describe this one, you would say n equals 5, p equals 5.51. It looks roughly symmetric there. Here's the picture of n equals 5, p equals 0.8. It's going to be skewed left in this case, is the shape of that one. So the mean is standard deviation. The mean, again, is the expected value of x. So now we need to learn standard deviation. This is a new thing here. So we've just learned, here it is, the standard deviation of a binomial distribution is n square root of n times p times q. When I say q, that's the chance of failure there. So 1 minus p is the chance of failure. P is the chance of success. So it's a pretty simple calculation. It is on our formula sheet. We don't have to memorize that for binomials. It's on there. These are for the mean and standard deviation only for binomial distributions, right? So let's look at this. So assume that 21 students at Mr. Hogarth's AP Stats class who did bottled water versus tap water activity was just guessing. So there's a 1/3 chance of guessing it correctly. X is the number of students who make a correct guess. It does seem binomial, right? And if there's 21 students, it's a fixed number of students. The probability is not changing each time. So that seems binomial. There's a distribution there, a picture of it. Calculate and interpret the mean. So the mean looks like, just looking at the graph, it's roughly symmetric. So it's probably somewhere around 7. Is there a way to calculate that? Well, 21 students, and it's 1/3. So the formula is, the mean is n times p is the formula. So if you didn't catch that on the previous page, the mean is n times p, or the expected value is n times p. So it's just a calculation, n times p. So n is 21. Probability of success is 1/3. So n times p is 7. And that's what I was guessing. I thought it would be around 7, and it was exactly 7, right? So you can actually calculate it exactly. You don't just have to look at the histogram there. So it would be about 7 would be the mean. Standard deviation is the square root of n times p times q. So n is 21, p is probability of success is 1/3, which means failure is 2/3. And you just type that in your calculator and you get 2.16. So that's the standard deviation of that approximately normal curve there. It looks like we now have a mean and standard deviation of an approximately normal curve, which would be nice. It's done without replacement. So that's just kind of a given. If it's simply without replacement, then it leads to a violation of the independent condition of binomial setting. So That's the case. So if you take sampling, but when it's large enough, a counter-successive SRS of site has approximately binomial distribution if it's large enough, and that's a key. So when taking a random sample of size n, a population size n, we can use a binomial distribution if, as long as the n that we sample from the population of capital N times 0.1, so as long as it's less than 10% of the total amount of things produced. So if we were sampling, it has to be less than 10%. So the problem is, like, let's say they made a special run of pink M&Ms. I don't think they really have pink M&Ms, and they produced 1,000 of them. So let's say we had a couple of, Costco-sized bags that potentially had some of these M&Ms in it, and we find out that we have, say, 200 M&Ms in our sample that we have of the pink M&Ms, 200 out of the 1,000. Because it's such a large portion of all the M&Ms that have ever been produced that are pink, it has a huge effect. They're not independent of each other. Whereas if millions of pink M&Ms have been produced and we have 200 of them, that's not a big deal. It's still basically independent. When you eat a pink M&M and you find another one, there's so many that it's inconsequential. If it's less than 10%, we're like, we're not going to worry. We're going to say that's independent enough, even though it truly, if you're not replacing the M&Ms you took and sampled, technically that's without replacement, and it technically wouldn't be independent. But if it's less than 10%, we just say, you know what, it's going to be okay. We can do that. So that's the less than 10% condition we're looking for. Okay, so in a survey of 500 U.S. teenagers aged 14 to 18, they were asked a variety of questions about personal finance. This should be interesting. One question was asked whether teens had a debit card. Suppose that exactly 12% of the 14 to 18 age group have debit cards. Let X equal the number of teens in a random sample of 500 with a debit card. Explain why X be modeled with a binomial distribution, even though the sample was selected without replacement. So we sampled exactly 12%. So in a survey of 500 U.S. teenagers. So we sampled 500 U.S. teenagers. Well, how many U.S. teenagers are out there? Are there more than 5,000 U.S. teenagers in the entire United States? I would say yes. So since that's far less than 10%, even though we sampled without replacement, it passes the less than 10% condition, and we are okay. Use a binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. Okay, so first, 500 is less than 10%. So then you're going to say, what is n? N is 500. That's the sample size. P is the probability of success, which is 12%. I want to find out what's the probability of getting less than or equal to 50. It says 50 or fewer. So you use binomial CDF because it's a range of values. And I don't love the way they wrote that. So I think this is from the 84 there, the notation of that. So let's just look at what it would look like on our calculator. So let's go to binomial CDF. So menu 55B, I believe, is CDF. And so we're going to say n is 500. Probability of success is 0.12. Lower bound is 0. Upper bound is 50. So we would actually put in the upper and lower bound there. And say okay, and see if I get the right answer. 0.0932, which is what they got as well. So again, so you would have a lower bound, upper bound. Instead of just saying X value, lower bound, upper bound. I think the 84 calculator that some of your friends may have at other schools doesn't have a binomial CDF on there, if I remember right. So Spire is just a little bit better than the 84, and it has a few more commands than the 84 does. This topic is not required for the AP exam. Some teachers prefer when presenting the sampling distribution of p-hat, chapter 7. So let's just talk about it for a second here, but it's not on the AP exam. That's nice to know. As the number of observations of n gets larger, the binomial distribution gets closer and closer to a normal distribution. So if you look, if n is 10, it doesn't look that normal. When n is 20, it's starting to look a little bit better. When n is 50, if you look at that graph, that red line is the approximately normal curve, or the normal curve there, and it does look like a pretty good approximation. It gets better and better. The bigger n is, the more likely we're able to use a normal distribution to model the data if we wanted to. Now we can also just use binomial PDF or binomial CDF, that binomial theorem essentially. When n is large, we can use the normal probabilities to approximate that. So that's true. This is called the large counts condition. So to test this, it's going to be NP greater or equal to 10, and then Q being the probability of failure, also greater or equal to 10. That is, the expected number of successes and failures are both at least 10. That's the large counts conditions. We do this, I think, more probably second semester than first semester. Not too concerned about this right now, but this is really nice to know that they're already showing this, this formula to us. So the condition is called large counts. Okay, so a survey of 500 US teenagers, again, same situation. One question asked whether teen has a debit card. 12% said they did. Okay, got it. Justify why X can be approximated by a normal distribution. So in order to have a normal distribution, N has to be large enough. Well, N is 500. Is that large enough to approximate a normal distribution? You would say, yes, it is. So I think that's okay. Use a normal distribution to estimate the probability that 50 or fewer teens. So again, we'd have to calculate the mean, n times p. So n is 500 times p is 0.12. Multiply those to get the mean. Standard deviation is square root of n times p times q. So square root of 500 times 0.12 times 0.88. You get those mean and standard deviations there. And now we're just going to do our, so the counts. So to identify that the large count conditions, you had to do n times p, which is 500 times 0.12, which was 60. So we expected 60 successes, which is greater than 10. And we expected 60 failures, because n times q is failures. There would be 440 failures, which is definitely greater or equal to 10. So because of it affects both, it affects, so the large count condition here, both successes and fails are expected to be greater than 10. We can go ahead with the normal distribution. Once you recalculate those mean and standard deviations of 60 and 7.266, then you're going to do good old-fashioned norm CEF here. So you're finding the lower bound is, it says the 50 or fewer teens, right? So I think I would use this one. This is the way I would do it. So I would say 0 to 50 is the lower and upper bound. Mean is 60. We calculate that right there. Standard deviation is 7.266. And we get a 0.8 or 8.4%. So what is a geometric setting? I feel like this is kind of the main part of this lesson, is we have to be able to do geometric. So not just calculate mean and standard deviation for binomial, but now geometric. So that's when we perform independent trials, same chance process, and record the number of trials it takes to get one success. So I think of geometric, if you want to put this in your notes, the first of doing something. So I keep rolling the die until I get a 6 for the first time. Or I keep flipping a coin until I get a heads for the first time. Each trial, the probability of success must be the same. But again, think of geometric as the first, how many times it's going to take to get the first of something to happen. That's typically what geometric is. So the number of trials, okay. So here's the formula for geometric. So this is the probability formula. So it's Q, which is the 1 minus P, is the probability of failure, to the K minus 1, where K is the number of successes, and P is when you, K is the value you want to have the success on, and P is the probability of success. So let's try this. Mr. Lochelle's class decided to play a lucky dart game. Student will be selected at random from your class, asked to pick a day of the week. Example, Thursday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If a student picks the correct day, the class will have only one homework problem. If a student picks the wrong day, your teacher will select another student from the class at random. Repeat the process. This game continues until a student correctly picks the lucky day. Y is the number of homework problems the class receives. Find the probability that the class receives exactly 10 homework problems as a result of the lucky day game. Okay, so they're going to keep going until someone guesses the day correctly, right? So the teachers come up with, rand int from 1 to 7. You have to kind of guess the day correctly. So we could use that formula, I think. So 1 minus p, the probability of guessing it correctly would be p is 1/7. So incorrectly would be 6/7. So 6/7 to the k minus 1. So I want it on the 10th term. So I think this would be the 10 minus 1 power times 1/7. So let's see what the answer is. So first is, is it, does it pass the test? So n is 500, p is 0.12. Because NP, probability of success and failure, we already figured this out. It is a normal distribution. Is that the same problem? This is not the same problem, is it? So that was bad information there. Okay, so find the probability that the class receives exactly 10 homework problems. Let me fix this here. Okay, sorry, I fixed the mistake there. So you can actually do this two ways. So the first way is what we mentioned using the formula. So the formula, again, to go back there, was 1 minus p, which is q, the probability of failure, to the k minus 1. K is the number you want the first win to be at, the first success on the 10th toss or the 5th roll of the die or something. So that's the value of k, and p is the probability of success. So you do failure to the k minus 1 times the probability of success. And because it kind of makes sense, if you think about it like a slot method, maybe this will make the formula make sense to you. So in this case, we want to have, I think 9 failures, right? So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these all need to be failures. This one needs to be success, right? So what's the probability of failure? Well, 6 out of 7 times I'm going to fail when I'm playing this game to try to get less homework problems. 6 out of 7, 6 out of 7, 6 out of 7. I'm getting tired of writing this. All those 6 out of 7s. Success would be 1 out of 7, right? So how many 6 out of 7s do I have? I have 9 failures. That's where that 6/7 to the 10 minus 1 comes from. But I have my first success on the 10th toss. So if you remember slot method, this formula actually should make some sense in your brain. There's also a way to do this in the calculator. Isn't this beautiful? So I love being able to have a calculator command that does this for us. So to do this, you go to your calculator, hit menu 5, distributions, and scroll up. It's easier to scroll up to geometric PDF. So it gives you a wizard there. What's success? 1 out of 7. When do you want that success? Essentially, where's your k value there? It is going to be at 10. I want the first time I win to be at 10, and it gives you the answer of 0.0357. So that's the way to do that. Part B, it says find less than 10. Now, this would take a lot of work to do this by hand. You'd have to do that formula, I think, 9 times. Plug in 0 for k, 1 for k, 2 for k, 3, all the way up to 9. And add all those up. Wow, 9 or 10 times there. So you got it. That's what they did, right? They plugged in all those values. 1, 2, 3, 4, 5. I guess they didn't plug in 0. Let me see why. seems like it go from 0. I don't know why it didn't show 0 there. It should have shown the probability of 0 happening first there. Maybe just because it ended up being 0, but they didn't show that. There's also a way to do this in the calculator, which is probably the way I would expect you to do this, because that would be a lot of work that way. So menu 5.5, as you scroll up, you can see geometric CDF, just like binomial CDF. When it's a range of values, always choose CDF. So 1/7, still the chance of winning. Lower bound 0, upper bound's 9. We don't want to get 10, we want to get less than 10. And it should give us that answer of 0.750265. Which means there's about a 7.75% chance that the class will get fewer than 10 homework problems by playing the Lucky Day game. So if they normally get 10 homework problems, that would be a pretty good chance they're going to get less than that, but there's a chance they could get more if they play that game. So this is on the TI Inspire. And I think I already showed you this. It's just saying PDF when it's just one value, CDF when it's a range of values there. So that's the key thing to remember with those geometric commands. The hard part is recognizing that that it's geometric, or that it's, by the way, so this is actually, I guess, technically, this is, it just says geometric like that. That's actually the command. Okay. This one. So describing the geometric distribution, shape, center, and variability. So if it's geometric, what's the formula going to be? So if it's skewed to the right, center, expected mean, expected value is around 7 there. They receive, it looks like that might be about the mean. So how do you get that? How do you calculate that? Variability is that. So I don't think they've done the formula. Here it is. Here's how you get those things. So you need the formulas to calculate that. So if it's geometric distribution, then the mean is 1 over p. Okay, so let's think about that. So in this problem, the mean was, p was 1 out of 7. So 1 divided by 1 over 7 is actually 7. The mean is exactly 7. That's kind of interesting. So you just kind of take the probability of success and flip it, essentially, is what you're doing. You find the reciprocal of the probability of success is the mean for geometric. It starts to make sense after a while why that would work. And then standard deviation is not as intuitive. So it is just a formula. It's Q, square root of Q up top. That's the probability of failure, square root of the probability of failure, divided by the probability of success. So that's just a formula you're going to use to get that. Okay, so let's try one. Local fast food restaurant is running a draw 3, get it free lunch campaign. We talked about this a few minutes ago. Calculate, interpret the mean of, so in this case, this does seem geometric, right? Because you keep on going until the customer must pay the bill. So how many customers does it take until you get the first free order? So that word first is a key that is geometric, assuming all the conditions are met. So calculate and interpret the mean of x. So the mean, the formula is 1 over p. So the probability of success here is there are 4 out of 52, or simplified 1 out of 13, if you simplify that fraction. So there's a 1/13 chance. So I think the 13th person would be the mean there. And it is, right? It's 1 over, again, 452 is the same thing as 1 over 13. So you're finding the reciprocal of that to find the mean. If the restaurant runs this promotion on many days, the average number of customers it would take to get the first free order would be about 13. What's the formula for standard deviation for geometric? I think it's square root of Q divided by P. So square root of 6/7 divided by 1/7, essentially. Sorry, this is square root of 12/13 divided by 1/13 is, I forgot the problem we're talking about. We're not doing the days of the week. This is the draw 3. So there's a 1 in 13 chance. So square root of 12/13 divided by 1/13 should be 12.49. just to show you that I'm right on that, I think I'm right. So if you did a fraction, and in the numerator, you typed in square root, oops, so square root of 12/13th divided by 1/13th. And it gives you the exact value there. Whoops, I don't want that. So it's 12.49. If the restaurant runs this promotion, you're going to have a mean or standard deviation of about, typically varies by about 12.5 from the mean of 13. So that guy asked each student in her AP Stats class to toss a coin and record the result. There are 28 students in the class. Assume the coins are fair. Let x equal the number of coins that landed heads. Here's a histogram. What is the probability does x have? Justify your answer. So 28 students. So, so we know that so this seems, is this geometric or binomial? So it's not talking about the first of something. So my thought is maybe it's a binomial. Success is flipping a heads. So it looks like the formula would be n times p. So n is 28 times probability of heads is 1/2. So I think 14 should be the mean, and that does look to be the case. Standard deviation is square root of n times p times q. So square root of 28 times 0.5 times 0.5. And you would get, but we know n and p there. Is it independent? So it passes all the tests. It's definitely binomial there. Describe the shape of the distribution. I'm sorry. So shape would be approximately normal or roughly symmetric there. Calculate and interpret the mean. That's what I was doing the first time there. So you use the formula NP is 14, and then square root of NPQ is 2.65. If the coins tosses were repeated many times with groups of 28 students, the number of students in the class who get heads would typically vary by about 2.65 from the mean of 14. Okay, a recent report from the Pew Research Center estimates that 71% of teenagers in age 13 through 17 use Facebook. Assume this claim is true. Suppose some researchers are going to contact a random sample of 300 teenagers to find if they use Facebook. Let x equal the number of teens in the random sample size 300 who use Facebook. Explain why x can be modeled by a binomial distribution even though the sample was selected without replacement. So the sample size was 300, that's relatively large. So NP would be 300 times 0.71. So let's see what that is. So 300 times 0.71. Hopefully that's bigger than 10. It is. And then 300 times the probability of Q, which would be 0.29, is also bigger than 10. So they're both bigger than 10. It's a large sample size. I feel very comfortable using the binomial distribution here because it meets the large counts condition, and it's less than 10% of the population of all U.S. teenagers. I forgot to say that. So it meets both conditions here. And they also use binomial CDF. It's a range of values. In this case, if you want to get 200 or more teens, so actually, if you use CDF on the Inspire, it's going to be a lower bound of 200, upper bound of infinity, or 300 if you want to. It doesn't really matter if you use 300 or infinity in that case. Use a binomial distribution. So we're just going to, do it that way. Okay. The Pew Research Center estimated 71% of teenagers use Facebook. I assume this is true. Suppose the researchers are going to contact a random sample of 300 folks. Explain why justify why x can be approximated by normal distribution. So it's going to pass two conditions. So is 300 less than all of U.S. teenagers aged 13 through 17? That's less than 10%. Passes that condition. Then you're going to do 300 times 0.71, 300 times 0.29. Passes that condition. It's large enough there. So use a normal distribution to estimate the probability that 200 more teens. This is really, so this one we used, I just want you to see, we used binomial CDF. We got 0.956 as our answer. Here we're using the binomial, we're using a normal distribution, calculating the n, the mean and standard deviation, and plug it into the norm CDF. We got an answer very close. That answer is 0.95, the other answer is 0.956. Just a different way of approximating this answer. So you could use either way. Again, right now, this is not part of the AP curriculum, this part right here, for this section anyway, but we may see it later, which it may come into play. But we can just use the binomial CDF for AP purposes for the test. Australian official lotteries has scratch-off instant lottery tickets can be purchased for $1. Probability of winning a prize is 1 out of 4. That's independent. It seems to pass some of those conditions. Mr. Urban decides that he will buy lottery tickets until he finds a winner. Until he finds his first winner. That sounds like a geometric. Then he's going to quit. The probability is the same. He's going until he finds his first win. Find the probability he buys exactly 8 lottery tickets. So you've got to figure out the mean and standard deviation here. So the mean would be the reciprocal of the probability of success, which is 1 out of 4. So 4 is the mean. I think it's square root of the 3/4 divided by 1/4 is probably the 8. So again, to get that, we could use technology there. So let's use technology and try it. So this is definitely geometric here. So menu 5.5, geometric PDF, because we want exactly 8. So probability of success is 0.25. We want 8. So it should do it for us. As long as we label what those two things are, we get the right answer. That's plenty of work for that one. Find the probability they would buy at least 5. So again, this is going to be a case of using geometric CDF. So menu 5.5, I think I. So 0.25 or 1/4, lower bound, at least 5, all the way up to at least 5. So we could put infinity, right? This is the CAS calculator, so I can't get to it. So I'm going to put a really big number. There's something on my screen stopping me from getting there. So I got that. Let's see what they got. 0.3164. That seems good enough. They did it by hand, right? They found the probability of 5. I see what they did. They actually found the complement of, so they said, what's probably getting 0, 1, 2, 3, and 4? And then they added those up and subtracted it from 1 to find the complement, which is getting 5 or more. So they used that sneaky technique to get that. We got it just using the command in the calculator. Beginning of the class, Mrs. Gauss plays a simple game where students earn extra credit. Each round, she rolls a single die. If the die shows a 1 through 5, the game continues to the next round. If the die shows a 6, the game is over. The first 6, and it's over. The class can earn as many extra credit points as rounds played. Calculate the mean number of extra credit points the class earns on a randomly selected day. Interpret this value. So what's the mean going to be? Is this geometric? So does it sound geometric there? The probability remains constant. First time you roll a 6 is 1 out of 6 chance there. So 1 out of 5 is failure. Success is rolling a 6 essentially. So when is it going to happen? The mean would be, I guess, would be 1 over the probability of success. So 6 would be the mean, right? And then standard deviation is square root of failure divided by success. So the mean is 6. That's calculate the mean number of extra points. Calculate standard deviation, just use that formula. And the formula would be, again, it's the fraction, the square root of the probability of failure, which would be 5/6, divided by probability of success, which is 1/6, and we get 5.4277. Calculate the standard deviation, interpret this value. So typically, the amount of extra credit point earned will vary by about 5.47 from the mean of, I forgot the mean, from the mean of 6, I believe, in this setting if many trials were performed. Okay, that's your lesson for today.